Okay, let me start. So, hello, dear all. I'm really happy to see you, Silvio, once again, and thank you very much for accepting our invitation. Welcome, everyone. The NFEL Armenia initiative is happy to have you during our discussion. Hope everyone out there is safe and sound, wherever you are. Today, we are hosting Silvio Sparano with a discussion about solar thermal energy technology and applications for Armenia. Silvio is a senior professional with 20 years experience in the oil and gas industry, both in the upstream and downstream. Since May 20, I will add from my side, Silvio is a great professional in economics, finance, trading, a very diversified and great professional, my professor in the past. So since May 2021, he's in charge of the development of the oil and gas business for TVP Solar company of Switzerland. And yeah, it's an innovative Swiss company in the industry of thermal solar energy. The presentation will be moderated, basically will be moderated by me, co-founder and co-chair of National Future Energy Leaders Armenia, but sorry, I may have troubles with my internet connection. In this case, Hasmik Barsarian will support us. After the presentation, we will have around 30 minutes for Q&A and discussion. We have questions received via various sources. So, and please ask questions as well in Zoom online. Welcome, Silvio. The floor is yours. Please share your presentation, share your screen.
Here we are. Okay. Can you see it on the screen?
Yes, yes, perfect.
Okay, let's start. Well, first saying, when we talk about solar thermal energy, we are interested to heat and not to electricity. They're both form of energy, but of course they are different. Photovoltaic panels produce the electricity. Solar thermal panels produce heat. We have to consider that heat is the largest global energy use. Just to give you an extent, if we take the share of energy consumed in the industry, consumes 32% of the energy worldwide, and 74% of this energy is heat. And the vast majority of heat in industry, more than 90%, is made with fossil fuels. So if you make a brief calculation, 2% is industry, you make 74% of it, so you have something like 21, 22%. 22%, the 90% of it is made with fossil fuels. So basically 2% of the energy consumed in the world is heat for industrial purposes and is made with fossil fuel. What is the solar thermal energy? Photovoltaic panels harvest solar energy to produce electricity. Thermal solar panels harvest the solar energy to produce heat. We have to consider one thing. The yield of photovoltaic panels is in the range of between 15 and 20%. The yield of thermal solar panel is much higher, is up to 55, 60%. So if the final objective is to produce heat, it's much better to use a solar thermal technology rather than photovoltaic, because the first one has a higher efficiency. The different solar thermal technologies are classified depending on their ability to absorb solar radiation. Solar radiation is made of two components. The component which is called direct and the component which is called diffuse. To make it simple, the direct component, for the direct component, you need to have bright sun. You have the diffuse component even when the sun is covered by clouds. Now, depending on the radiation that the technology used to harvest energy, we classify the technologies. Basically, solar thermal technology are classified in two kinds, concentrating and non-concentrating. When they are non-concentrating, your panels are flat. When they are concentrating, your panels are made with a curve so that they can concentrate the energy. And depending on the technology, you can have temperature that can be as low as 35 degrees or as high as 500 degrees, with different, of course, applications. In this graph, in this picture, here we have three. You have on the top, you have flat technologies. On the bottom, you have a concentrating technology. Flat technologies use the entire spectrum of light, diffuse and direct light. They can harvest from ultraviolet, from infrared, and from visible light. Concentrating use only the direct fraction of solar radiation. The difference between those two technologies are different in the respect of their efficiency. Non-concentrating technology have high efficiency but achieve lower temperature. Concentrating technology achieve higher temperature but lower efficiency. There is also a second difference. Non-concentrating technology require little maintenance. Concentrating technology require a lot of maintenance because we keep the mirror, you see here, the mirror have to be kept clean all the time. So in location, such as in a desert or where you have accumulation of moisture during the night, those technologies in practice do not work. What is the place that Armenia can carve in this technology? Well, the first thing that we have to consider is that Armenia has notable solar energy potential. Compared to a European country, there is a very good horizontal irradiation in Armenia. To give you an order of magnitude, in Armenia, we have in the range of 1,700 kilowatt per hour per square meter per year of irradiance, which is 20% higher than the most favorable location in Europe. This is the reason why the government in Armenia is focusing in investing massively in solar plants, because there is a sun. In this respect, the government has declared that their objective is to achieve 15% of electricity produced with solar power by 2030, which is equivalent to 1.8 billion kilowatt per hours, or if you want 1.8 million megawatt per hour. This is a very big number, a lot of energy. I might confess that I'm a little bit skeptical that they can achieve so much solar energy by 2030, but it's an ambitious target. All these projects are for photovoltaic solar energy. So for the production of electricity. But in a few minutes, we will show that there is a massive potential for thermal solar energy in Armenia, because there is consumption and there is the sun. A few words about the situation of energy in Armenia. Today, Armenia faces three challenges. faces three challenges. So there is a gap between supply and demand. There is a supply. There is an issue of reliability of the existing source of energy, and I think that in this respect, the unique nuclear plant in Armenia will pose a challenge in a number of years, because it is under increasing scrutiny from the international agency about its security. And there is, of course, a need for the country to maintain affordable tariffs. This kind of issue is getting more and more stringent with what's happening in the international scene with the war in Ukraine, and of course, what happened after COVID. It is difficult to get supply of energy at affordable tariff. This issue is also made more stringent because Armenia has limited energy resources. The only one that is consistent is hydroelectric power, but it is the only one and cover only 35% of domestic electricity consumption. All the other comes from nuclear, from the unique nuclear plant in the country, which use fuel that is enriched in Russia, and the balance is made of consuming oil and natural gas, which are imported from Russia, Iran, and Europe. And I guess also marginally from Georgia, some refined products. When we look to the energy mix in the country, we notice that a lot of electricity is also used for heating, which is, of course, is a shame, because if the idea is to use electricity for heating, we could make the energy for heating directly with thermal solar and reserve the electricity to another use. Let's see what is the part of this heating in the energy mix. In 2018, the residential sector in Armenia accounted for 30 petajoule of energy consumption. 30 petajoule corresponds, I think, to 2,200 megawatt per hour. And this 30 petajoule of energy consumption was about a third of the overall energy domestic demand. So you see that curve on gray, it represents the residential consumption of the country. It is 34% of the overall energy domestic demand. So 1/3 of the demand in Armenia is for the residential sector. And this 34%, 2/3 of it, which is 20 petajoule, it's used for heating, water heating, and cooling. So there are 20 petajoule that can be supplied using solar thermal panels. We can see the split. On the left, we have the energy sources used for the heating. On the right, you have the energy used for producing hot water. And you can see that most of it, heating and water heating, are made with natural gas, but there is also a non-negligible quantity of electricity that it's used for this purpose. Again, those two consumptions can be easily replaced with solar thermal panels. So let's come to the role that TVP Solar can have, and in this respect, I want to return again to the second slide. You can see that we have basically 4 technologies in solar thermal power. Now, let's take out of the discussion the last one, which is the one with the concentrating technology, parabolic through Fresnel collectors, solar power, solar towers, sorry. I want to remove this one for one reason. They are extremely expensive. You achieve high temperature, but you require a lot of maintenance, you require a lot of investment. Until now, they have not proven financially, economically sound. They work with a lot of maintenance, but they are very costly. The other three technologies, they are cheaper and they require little maintenance. And in particular, the third one, the so-called high vacuum flat plate collectors, on top of being not too expensive and requiring little maintenance, can achieve a maximum temperature of 170 degrees, which is a temperature that is high enough for a number of civil and industrial purposes. This is the segment where TVP Solar has decided to operate. So TVP Solar is a Swiss company which produced thermal panels, which operates under vacuum. Let's explain what does it mean they operate under vacuum. Let's imagine that you have your thermal solar panel, okay? And let's imagine that in this thermal solar panel, you have created the absolute vacuum. A vacuum so deep as it is in the sky, okay? In the space, in the outer space. Zero molecule, there is nothing. Completely vacuum, completely void. You follow me? And let's imagine that you have energy that is impacting the panel. As in the panel, there is absolute vacuum, the energy cannot go anywhere because by definition, the vacuum does not transmit by convection and by conductivity. So once the energy gets in the panel, cannot get out because it's completely isolated by the vacuum. So the energy can only go through the tubes which are in the panel where the water or the oil, depends on the fluid which is chosen, it's circulating. This makes all the energy concentrating into the fluid which is circulating in the panel and make the temperature very high because all the energy is concentrated in a little volume of liquid circulating in the panel. Playing with the quantity of liquid that is circulating in the panel, we can have a higher temperature if we have a small flow of fluid in the panel, or we can have a lower temperature if we increase the flow of liquid in the panel. This is the reason why with this technology we can achieve the highest efficiency and the energy output in any climate condition. To give you an order of magnitude, if the idea is to produce pressurized water at a temperature of 120, 130 degrees, we have a yield of 50%. This makes possible the energy produced with the solar thermal panel can be used for a wide range of activities, wide range of applications. They can be a general application or industrial application. We can use this energy for district heating, residential heating, production of hot water, pasteurization, drying, fermentation, bleaching, cooking, air conditioning, fluid separation, crude desalting. Wide number of applications. I have not listed all of them, but they are about 100. What is the cost of the energy produced with this technology? You have a full cost, which is the sum of the depreciation of the investment and the operating cost to operate the technology. We have a cost which is between $11 and $25 per megawatt per hour. We can achieve 11 in countries with very high irradiation, such as in the Middle East or at the equator, and we will be at 25 in a Europe. I think that in a country like Armenia, we should be at around 18, 20. So 1 megawatt per hour of heat produced with TVP Solar has a full cost, depreciation and operating cost, which is around $18-20 per megawatt per hour. And of course, on top of this gain, there is also the gain of CO2, because this technology does not produce any CO2. So theoretically, it is also possible, if your company is operating on a regulated market, to sell the credits because you are producing energy without generating CO2. Those kind of solutions can be easily integrated to existing equipment. And we can make a number of things. We can make hot water, we can make pressurized hot water, we can even make steam. One of the possibilities to produce pressurized hot water, and after to pass in a valve and depressurize the pressurized hot water and make steam. I see there is a question now from Shant, who asks me, can you repeat the investment cost per kilowatt per hour? Okay, take this way. 1 megawatt per hour of kilowatt per hour. It was for megawatt per hour. So megawatt per hour, the investment cost is maybe $15 per megawatt per hour. So you have to divide by 1,000. The investment cost is 15, and you have to add maybe 3 for the operating cost. So the investment part is $15 per megawatt per hour, and the investment has a lifespan of 25 years. One important thing, concentrating technology operate with mirrors. So we have the light that goes on the mirror, and after it goes on a place where you have the liquid to heat. Flat panels, and in particular vacuum flat panels, they do not operate with mirrors. So it means that they do not require the same level of very high maintenance, and they do not require continuous cleaning. To give you an idea, you can see in this image, you have panels at the beginning and the end of 1 year cycle in the desert. Even when the panels are completely covered with dust, they only lose 7-8% of efficiency. So they require little maintenance, and at the end of their lifespan of 25 years, they can be recycled at minor cost because they are made of 100% fully recyclable material. TVP Solar only started operation in 2018, but our portfolio is increasing every month. In 2021, we have signed the EPC, engineering, procurement, construction for a large solar field in the Netherlands near Groningen. It will be 48,000 square meters and will produce 25 gigawatt per hour of energy per year. And I want to insist that this infrastructure will be made in the Netherlands, where you have very, very little irradiation. To give you a number, in the Netherlands, we have an irradiation of 1,050 kilowatt per hour per square meter. In Armenia, we have 1,700. So we have 70% more. So it means that an investment in Armenia would have a payback 50 to 70% faster, because the production is 50 to 70% higher. This investment will be the third largest solar thermal plant in the world. Now, in the next two slides, I will show you what is the potential for Armenia. Decided to invest in thermal solar energy. As we've seen in the previous slide, I want to show you again just to make you the connection. In slide 8 and 9, we have seen what is the share of natural gas and electricity used in the residential sector to make heat. When we elaborate those numbers, we find that 64% of residential heating and 88% of heat water is made using gas and electricity. The sum of these two are estimated to a sum of 8 petajoule per year, which means 2,200 gigawatt per hour per year. If we decided to deploy solar thermal power to replace 20% of this 2,200, we would replace the consumption of 440 gigawatt per hour per year. So the question is, how many solar panels do we need to generate 20% of this energy? So, or how much solar panel we need to install to generate 440 gigawatt per hour in a year? The calculation is the following. In Armenia, we have an average irradiance during the year of 1,720 kilowatt per hour per square meter per year. And if we want to produce residential heating and heat water, we need to operate at 110, 120 degrees. In these conditions, we have a yield of 55%, so we can harvest from each square meter of panel during the year 0.945 megawatt per hour per square meter, almost 1 megawatt per hour per square meter. So if we divide 440 gigawatt per hour by the unitary yield per square meter of panel, we find 465,000 square meter of solar collectors. This amount of collectors, 465,000 square meters, would generate the energy. But after this energy, you have to store, because you need to accumulate for the night, and you need to distribute to the users. So you should invest into some additional infrastructure. The full investment for the 465,000 square meters of collectors, plus the distribution network, the storage, would be in the range of 300 million euros and would generate 440 gigawatt per hour per year of renewable energy. Based on the actual energy content of natural gas, this would equate to a saving of 49 million cubic meters per year and would reduce the emission of CO2 of almost 100,000 tons per year. This means that you can make a small calculation. I don't know what is the cost of natural gas in Armenia these days, but I can imagine that it should be in the range of maybe 40-50 cents per cubic meter. So if you multiply 49 million by 50 cents per 50 cents per cubic meter of natural gas, you should generate, only with the saving of natural gas, in excess of 25 million euros. And on top of that, you have the gain for the CO2, because you are reducing CO2 that you can sell on the international market as a CO2 credit. So you could have, in terms of gain with an investment of this kind in excess of 30 million euro per year, which would make the payback of the project under 10 years. And of course, this would include also the creation of all the infrastructure of distribution of energy that, of course, would operating for much longer than the actual lifespan of the panels. I think this is for well, my phone number and my email is in the end. I think that now we will have some questions.
Thank you very much for your presentation, Silvio. Well, it's great. I have a question from my side, if you let me. Who's the main consumer, by the way, of this 25 gigawatt per year plant in the Netherlands? What's the consumption structure for this, if it's an open information, let's say?
No, it's not confidential information. It's an entire community, which means residential buildings. There is shops, a swimming pool, schools. So
How many people?
40,000 households.
40,000 households, so that will mean 120,000 people, roughly, yeah? Okay. And so please...
The entire city, the entire city.
Intercity.
The entire city.
Please switch on your microphones and your videos and feel free to ask your questions. You can raise your hands to be well organized this, yeah. Okay, Rudolf, please.
Hi, Silvio. Thank you very much for the interesting presentation. There's a question I just have regarding the numbers towards the end in terms of application to Armenia. So in terms of heating that is used within Armenia's energy mix, right? The figures that you gave, I might not be correct in the number that I'm saying, but as far as I know, 60 to 70% of it is used in winter and autumn time, right? So that's when it gets cold over here, and majority of heating systems work with hot water. So that's why the majority of heating is used over there. Having said that, the solar capacity factor average for Armenia in autumn and winter are between 0.2 and 0.25. So I'm just thinking in terms of that, given the fact that majority of the heat is used during winter and autumn, and given the fact that it's quite low, the capacity factor of solar, would this still be an investment or something worthy of it? If you see what I mean by that question.
Yes, Rudolf, thank you for the question. It's a common, of course, query. We have to consider a thing. If the objective is to make a temperature for district heating or for industry under 120 degrees, so if the objective is not to be higher than 120 degrees, even winter irradiation is large enough. Think, for example, in the Netherlands, they have the same problem, and they have 2/3 of the irradiance which there is in Armenia, and it's still largely enough to make 80 degrees. If the objective is to operate at higher temperature, to go at 150, 160, 170, in winter, it can be problematic. But for 110, 120 degrees, the panel harvests sufficiently to make it. Of course, in winter, it will make less, but it will still make enough, because if you want 120 degrees, you are just at the middle of the range of operation of the panels. I want to show you something. You see this curve?
It hasn't changed the screen for me just yet. I think it's because of my internet. Yeah, I think it's the right place now. Yeah.
You see this curve? Let's imagine that we are in winter, so we are on the right. which is not full sun, because we can imagine that in winter we don't have a full sun, isn't it? So you could imagine that at the left it's summer operations, on the right is winter operation. Okay. You can see that if the objective is to go to 100%, you have still 50% solar yield. And 50% of solar yield, it means you are operating at 250 watt per megawatt. You are operating at 250 watt per square meter, which is largely enough.
Yeah, that's
water at 100, 110 degrees. If the objective is to make steam, it will not be enough.
No, that's fair enough. That makes sense. I just wasn't sure about the efficiency of it, so that would probably work. But I'm assuming even in implementing it, you would need some sort of a side support technology to take over in case there's ups and downs, and also to be able to supply.
Okay. In this case, what we do is that we accumulate energy. You would have you install more surface of panels, and you install a storage of energy in the form of pressurized water.
Okay.
If you are over 100 degrees, if you are under 100 degrees, it's a storage of hot water at 90-95 degrees, which is this is commonly done. To give you an idea, this solar field in Groningen in the Netherlands, there will be a storage with hot water at 90 degrees of the capacity of 6,000 cubic meters.
That's quite a lot. Okay, that would make sense. So if it comes with storage, then I guess it's
yes,
it is possible to rely on that.
It must, yes, it must.
Thank you, Silvio.
Welcome.
Now we have a question from Shant Gregorian. Shant, please feel free.
Yes, also thank you from my side for the nice presentation. I have many questions, but I will limit it to two. Are we talking about a closed cycle coolant or water, or it's an open cycle? This is the first question. The second one, what is the smallest unit capacity? I mean, how small can this unit be in order to function? Thank you very much.
Okay, the first question is that it's closed loop. It's a closed loop, so it means that the panels will operate on closed loop, and it will open the panel operate on a closed loop, and it will heat up a secondary loop that it's open. So we recirculate in the panels always the same water, and through a heat exchanger, it gives energy to an open loop. Concerning the second question, the minimum size for a solar field of this kind, it's 0.5 megawatt. 0.5 megawatt, it means maybe in a location like Armenia, 500 square meters. This is really the smaller size to have a minimum of economy of scale.
Thank you very much.
Thank you. Thank you, Armen. Please go ahead.
Yes, thank you for the presentation again. I have two questions relating to Armenia. First is you mentioned the economies of scale and the need for storage. The heating in Armenia is mostly not done through district heating, because the system for district heating collapsed in the 90s, and now it's separate households, each having a gas boiler or something like that. So in not being able to benefit from that greater efficiency and economies of scale, what would you say the effect will be on Armenia? That's the first question. And the second question is, as you mentioned in the beginning, it makes more sense to take energy by solar thermal and use it for heating, as opposed to using electricity from photovoltaic. But from what I know, for example, in England, at some point, people were actually making heating using photovoltaic, because there were feed-in tariffs. So the electricity generation was subsidized, and it made more economic sense to use photovoltaic panels, even though it doesn't make sense, of course, from technical efficiency. And so my question is, do you see any such, from your experience, any such dangers of policy interaction between PV and solar and thermal, and perhaps if it could also have ramifications for Armenia?
Okay, well, let's just answer first the second part of the question, because I like it most. After I will answer to the first part. Guys, this is clear that when you have a very high subside on an energy, you end making, I would say, use of that energy even for use which are not natural for it. And we have observed that in the last 15 years that subsides on photovoltaic were so high that we ended with people using photovoltaic to make heat, even if this does not make any sense, just because government were paying for it. What can I say about that? I can't help. I mean, those kind of things, I can tell you something, are not lasting. In Western Europe, the tariff for the purchase of photovoltaic energy have already been revised, and they've been revised, I mean, they've been reduced, because the government was very eager to give a subsides when the percentage of photovoltaic was very small. But now in some countries you have 15–20% of photovoltaic capacity, and they are reducing the tariffs, of course, because they cannot pay for it. So my belief is that an energy should be competitive on a standalone basis. If you rely on subvention to make your energy viable, this will not last for a long time. Just to make it clear, there is this kind of problem in France with the nuclear energy. Nuclear energy is a powerful tool in geopolitical terms, because of course make you independent from the other countries, but it's very costly. When you enter the full cost of nuclear power in France is not what the people are paying. The real cost is much higher, but as the operator is state-owned, the people do not see it. Well, they see it in terms of taxation, because at some point you have to pay, but you do not pay on your electricity bill. You pay in your income tax statement each year. Not sure that people make the connection, but still you have to finance it. First part of the question, you need the common infrastructure to have thermal solar energy distribution. This is a fact, but I want to move forward about that. It's not because a country is moving to an electric car that does not need roads. You follow me? Even with electric cars, you need roads, isn't it? Well, this is the same. I mean, if the country, as in many, I would say, former Soviet Union countries, has neglected the common infrastructure of district heating, I think that now they should think about reviving the investment, because from an economic perspective, there is nothing of more efficient than district heating. It's very efficient. Much more efficient than individual boilers. And now I don't know what is the state of the infrastructure. Is it really so run down?
Well, from what I know, again, in the it used to be somewhere around probably 90%, maybe over 90% that was district heating in the early 1990s. But then from what I know, it dropped to almost zero.
But is it possible to recover this infrastructure?
Oh well, that I will not know. That would require. It's probably Soviet age infrastructure, so there will be question to what extent you can, of course, renovate it. But from what I understand, you're saying that district heating is something that would make sense to move towards, whether it's done through combined heat and power, or nuclear thermal, or solar thermal. And so you're looking at it in that sense, sort of.
Yeah, take it this way. During the 70s, the 80s in Europe, there was a lot of district heating. Okay. After district heating was discontinued because people wanted to install individual heating because natural gas prices were very low. In fact, the reason why district heating was abandoned and people went for individual heating is because natural gas arrived everywhere and it was cheaper to have individual heating based on natural gas. It could be individual in the building or individual even in the apartment. Okay, fine. But I think this is a fact of the past because natural gas is not cheap anymore. And whatever, this has to be very clear, whatever is the source of energy with renewable, heating has to be centralized on district heating. Even if you want to make it with another source of energy, whatever it is, you still need a common infrastructure because a renewable energy takes place. You cannot imagine to have that place on each user. This is the same for photovoltaic. It is not cost effective to have small photovoltaic panels on each house because you have a lot of costs that after are redundant, are repetitive. The cost of the inverter, the cost of the connections, a lot of cost. The maintenance is very high on a small solar field. But if you have a solar field of tens of thousands of square meters, it's different. But after you have the cost of the distribution, this is a common issue of renewable. Let's be very clear. It took maybe 100 years to develop a model of energy based on fossil energy. It's not going to take 5 or 10 years to move away and to switch to renewable. This transition will take decades. Maybe it will take, let's be very clear, when I listen on the TV, on the media, we are going to become zero neutral 2035, 2040, I laugh. Because I operate in the energy, I've seen, I know how much there is to do. When we mean energy, I think in my mind to all the infrastructure that has been built over 100 years. And to become neutral, it means that all this infrastructure has to be removed and replaced with a new one. It's not taking 20 years. It's taking maybe 2 or 3 generations, 50, 60, 70 years. So if the objective of Armenia is to decarbonize and to move to a cleaner energy, definitely reviving the existing district heating infrastructure, it's a step to be done. Whatever is the source of energy we won't use after, whatever.
Thank you. Any other questions from the audience? Okay,
Can I
so
ask one question?
yeah, sure. Please welcome.
Thank you for your presentation. Last year, Armenia used 2.8 billion cubic meters gas. From this, about 500 million used in electricity production and 800 population use. Your suggestion use solar energy. This not saving gas saving. What is investment? If we will be save gas and what how much we will invest for this solar energy?
Yes, the investment is, if we want to remove If we replace 20% of the domestic consumption for heating, this will save 50 million cubic meter of gas. If you want to replace 100%, it's 50 times 4, so it's 200 million. The investment is 300 million euros. In these 300 million euros, I have also put the cost to revive the district heating. Under reasonable assumption, because I still believe that some of the infrastructure can still be saved. Maybe the piping has to be removed, renovated. Maybe the pumps have to be replaced, but I still believe that the civil work can still be used. I mean, the trenches are there, they can be saved, all the traps, I mean, everything is there. I still believe that a lot can be saved. Maybe some piping has to be replaced, the insulation has to be saved, has to be replaced, but I still believe there is a lot that can be done. You know, in Soviet time, things maybe were not efficient, but they were hard. They were not made necessarily with the perspective of saving money. They were not efficient, but they were good quality.
Yeah, good point. And we have a question from Natalia Avanesova. Please go ahead.
Hello, Silvia. Thank you so much for a very interesting presentation. I have two questions. That site in Netherlands, do you know what sort of return it yields on an annual basis? And also, you just mentioned 300 million investment, which is required to revive the system. Like, do you know what return that would yield approximately?
First question, okay, in the internal rate of return for that project in the Netherlands is 8%.
Is that subsidized? Because that's quite high.
8%, it's not subsidized, but you have public investors that are investing in it. But Natalia, one thing, it was 8% based on the economics on 2021. Based on natural gas prices, now it's more, of course. But I also do not think that natural gas prices now have to be taken in future projects because they are very high, the prices now. If you use the price as they are now, all the projects are good. But this is not going to last for a long time. The current situation, it's not possible to continue. How much this situation can continue? 1 year, 2 years? Even that, I don't think more. You know,
you don't know what other war might happen.
Well, but you know, take it this way. In the past, we have already seen situation of wars, big conflict, Iranian revolution, big stuff happening. Okay, big stuff. Because what's happening now in Ukraine is big stuff. But if you think during the last 6 years, we had already events of this kind. And at some point, you must have that there is a solution. It cannot last forever. And the prices today cannot last forever. Or I want to say another way. Let's imagine, just to have fun, you know, let's imagine we were discussing we are all sitting around the table and we are drinking wine and we are having fun, you know, and we want to make a funny scenario. Let's imagine that this situation lasts for the next 15 years. If this situation lasts for the next 15 years, it means that the actual demand of natural gas will drop, because at current price, you can imagine that the whole system of consumption would change, exactly as it happened with oil in the 90s, in the 80s. I mean, before the Iranian revolution, people were using the car for everything. And it was after there was a completely switch of model of consumption. So either way, the situation will calm and the prices will go down, or the situation does not calm and the prices remain very high. At some point, this will induce a change in consumption. But prices cannot stay like that forever. From an economical perspective, this makes no sense. Every excess has a limit. We have already seen in the past in the energy market that when prices of energy are too high, after a number of years, they tended to collapse.
Okay, thank you.
Thank you.
And did you have in mind the return you've considered in the context of Armenia?
Yes, I want to tell you, where does it come, this 300 number? Okay, Natalia. We are talking a 465,000 square meter of solar connector, correct? A solar connector alone have a cost of around 400 euros per square meter. So if you make 465 times 400, you will find a number that should be just 465. You have 186 million euro. So to arrive to 300 million, this is the additional cost to reconstruct the district heating system and to make some storage of energy.
And have you considered grid constraints? And
not at 20%.
okay.
Because 20% is small. After, if you want to go at 100%, you get into grid constraint.
Okay.
But this, of course, would be progressive.
So if I understand it correctly, so we don't have grid constraints yet until it progresses.
At 20%, you don't.
Yeah. Okay.
At 20%, you don't. 20%, you don't. At 20%, you don't, because I must assume that the existing infrastructure, if it's revived with some investment, can take 20% of its nominal capacity.
That makes sense.
If you want to do more, of course, this will be different, of course.
Okay. Thank you.
So we are approaching to the end. Last or one of the last questions, Rudolf, please.
Just a quick question, and apologies for the background noise. Is there a line in terms of how big a city is, right? And this is not just directed towards the solar power plants. I'm also keeping in mind centralized heating system. So what you were saying in terms of localization, is there sort of a line in terms of how big a city is of after it becomes cost ineffective to go with such technology? Do you see what I mean by that?
Take it this way: the limit is the capacity of the capacity to transport the energy, which is fluid, which is water. Of course, when you exceed pipelines of 24, 28 inches, it starts to be ineffective. You have to multiply. So say this way: it depends on the volume that you have to transport. But of course, when you are bigger than 24 inches pipeline, you have to start to duplicate. You don't have any more economy of scale when it's bigger than that.
Okay,
So
makes sense.
it's really the capacity to transport is the infrastructure. It's the same as electricity. It's the same as electricity. At some point, you can't produce more than a certain amount because you cannot transport it any more efficient. You have to duplicate the lines.
Thank you.
Other questions? 1 or 2 minutes left.
If I can just jump in on the last question, and I think Natalia has actually perhaps a new question then, because I was going to comment, but if there is a new question.
So what is the question?
Natalia, do you have a question or just... okay. Okay. So let me check. Yeah, I'm just checking with the questions list to see whether there is any relevant. Yeah, I think most relevant questions were answered. So we're approaching to the end of our discussion. Once again, thank you so much, Silvio. It was really a great pleasure to see you. I invite you all to subscribe to our YouTube channel we recently started. You can see our previous discussions and stay tuned to our further ones. And today's event recording will also be uploaded soon. Additionally, I invite all energy specialists to join our communities, National Future Energy Leaders Armenia, or Armenian energy professionals for networking, having your contribution to the energy sector and youth development. Again, thank you all very much for joining us today. And thank you very much, Silvio, for being our guest speaker today. Have a good day and hopefully see you soon on our next events and discussions. Bye-bye.
Thank
Thank you very much.
Thank you to you all. Bye.